Today's lecture is going to be a little different than the typical 61B lecture. I wanted to give you a sense of what a theory class might feel like in computer science, so we're going to talk about things in a little bit more of a theoretical, a little bit more of a general manner than we usually would. So what we're going to do is talk about a new type of thing, a new graph problem, which is to find the minimum spanning tree. We'll talk a little bit about some theory, and then finally we'll talk about a couple of specific algorithms. Okay? So let's start by just defining things. So we'll start with what a spanning tree is. So given an undirected graph, a spanning tree T is going to be a subgraph of that original graph, where T has a few properties. One, it's connected. That means all of these pieces here and all of these pieces here are connected, right? There's no gaps. It's not two disconnected pieces. It's acyclic. Well, that means that there are no cycles. And it turns out then that makes this object we're constructing a tree, right? So if you have a connected acyclic graph, that thing is a tree. Okay? So those are the two properties that make it a tree. And then it also has the property that it includes all of the vertices. Okay? And that makes it spanning. That is, it spans the entire graph. And so as an example, which I've kind of alluded to implicitly while discussing these properties, for this graph right here, these black lines here constitute a spanning tree. Okay? And the gray edges are those which we haven't included in this particular spanning tree. Now there are many other spanning trees. For example, we could discard this 8 and add back this 9, and that too would be a spanning tree. However, that spanning tree would have a greater weight. What do I mean by that? Well, this spanning tree we can think of as having a total weight which is equal to 3 plus 1 plus 4 plus 7 plus 8 plus 8 plus 2 plus 2 plus 3. And you can think of that as the amount of, say, wires that it would cost to connect up each of these pieces. So, or say buildings, right? And so the problem of finding a minimum spanning tree is, you can think of it as the equivalent of what is the minimum amount of wire I can use to connect up a number of buildings directly, right? And in this case, we don't care about how far the distance between two particular points is. So if I go from here to here, yes, I could run a wire directly from this position to this one, but it's overall cheaper to run 3, 2, 8, 8. And because, if we're thinking about electricity, all that matters is connectedness. It doesn't really matter that there's not a direct connection between these points. Okay? Now, of course, this is not directly applicable to, say, the power grid, because you may want some type of redundancy and so forth, but I think it's a nice analogy. Okay? So here's a couple of spanning trees as examples. This is also a spanning tree. Even though it is a long line, it still obeys the property that it is connected, acyclic, and includes all the vertices. So this is a very spindly tree. Here's another spanning tree. So maybe ponder, how many of these are spanning trees? Okay, so you've thought about that a little. And so hopefully you convince yourself this one's disconnected, this one has a cycle, and this one's fine. So what good is a minimum spanning tree beyond some sort of fictional, non-redundant power grid design? Well, a couple of examples. One of them is supposedly network design. So on the left, we see a minimum spanning tree of the bicycle routes in Seattle. And supposedly this is somehow useful for us to understand how we might design a bike network. Though I have to admit, I don't quite get exactly why. But there's a link at the end of the slides and the citations if you want to check it out. But another one that does make a little more sense to me is in medical imaging. So suppose you have microscope images of cells, and you want to know, is this region of a person, is there perhaps cancer, right, at the microscopic level? These are not, and so what we'll do is maybe we'll mark each of the nuclei of cells. And so this is a relatively small piece of a person, because it has not many cells, as you can see. But what we might do is, given a bunch of nuclei, we could find the minimum spanning tree of all of those nuclei, where we draw a graph between two nuclei if the cells are touching. And in that way, we can determine properties of the minimum spanning tree, like how many edges there are, or, for example, what is the mean length of the edges in the minimum spanning tree. And so it's been found that in some clinical applications, features like the mean length of the minimum spanning tree can actually be predictors for cancer, even with a relatively small, as you can see, number of cells involved. Okay. So let's see if the idea of a minimum spanning tree makes sense. Now that we have some motivation, some basic ideas. For this graph, I just want you to find the minimum spanning tree. And I'm assuming this isn't going to be too crazy of a challenge. It's a very small graph, but just to check your understanding, give it a shot. Pause. Okay. And so hopefully you found this as the answer, that the minimum spanning tree is this set of edges. Okay. So make sure you understand that before you continue, otherwise the rest won't really make sense. So my next question for you is, how are the minimum spanning trees and the shortest paths trees for a graph related? So recall from the previous lecture when we talked about Dijkstra's, the shortest path tree tells you the path from a particular source to every other node in the graph. And so what I'd like you to do is ponder this question. Is there some graph whose shortest paths tree is also the minimum spanning tree for this graph? And try and come up with an answer based on these vertices, and pause and think about them. To solve this problem, let's try finding some shortest paths trees. So I'll pick an arbitrary start point, let's say D. So we find the shortest path tree from D. Well, the shortest path to A will be direct. From D to B will be direct. And from D to C, also direct. There's no need to use this edge in the shortest paths tree. Okay? So if we look right there, this is the shortest path tree from D, if S is the source, or sorry, if D is the source. And we'll see that is not the minimum spanning tree that we just saw. So you can repeat that exercise for each of the 4 starting vertices, and we'll see that we get 3 different shortest paths trees. This one that we just saw, and finally this one right here. And so this shortest paths tree is the one for B, and is the only one where the shortest paths tree is the same as the minimum spanning tree. So let's compare and contrast MSTs and shortest paths trees. We can say that a shortest paths tree depends on the start vertex, because what the shortest paths tree tells you is how to get from a source to everything else. There's no source for an MST. There's no notion of a start place. But nonetheless, it so happens that the MS tree sometimes happens to be a shortest paths tree for some specific vertex. Okay? So in this case, it happened to be the one from B, happened to also be the minimum spanning tree. All right, now I got a challenging one for you. Given this tree shown, give a valid minimum spanning tree for the tree below. And so a pretty hard question, or maybe a hard B level, maybe even an A level question is, can you find a node for which the shortest paths tree is also the minimum spanning tree? So give that a shot. Maybe think about that one a little bit, and then I'll spoil it in just a moment. All right, so if we look at this problem, the minimum spanning tree, if we want to just draw that, is going to be the following. It's going to involve both of these nodes that have, or both these edges that are 0, 8. There's no better way to connect everything up than this one. Okay? Now the harder question is there a particular node that if we find the shortest path tree from that node, we recover the minimum spanning tree? And so here's my kind of janky, it's not a full proof, but this is my kind of proof that it doesn't work. So I hope you'll agree that the minimum spanning tree can only use 2 of these weight 2 edges. However, if you find the shortest paths tree from any vertex over here, you're going to have to use both of these 2s, because it would be going out of your way to wrap around this edge and use this 0 edge. And so if you use any of these 8 as your shortest paths tree, then you'll have to use both of these. If you use any of these 8, you'll have to use both of these. And if you use the middle, well, in that case, you're going to have to use 2 on one of the 2 sides. Okay? Or sorry, rather, if you do the shortest path tree from here, I apologize, then you'll actually use all 4 of these 2s, because the shortest path would then be to not go around either of the edges. Okay? So that's an argument that there are some graphs for which there is no source vertex whose shortest path tree is the minimum spanning tree. And the reason I bring that up is because I want to draw a distinction between these 2 types of trees. The minimum spanning tree is not necessarily a shortest path tree. Okay. So that's a little more technical detail than we'd usually do for a topic. But for this one, again, since I kind of wanted to talk a bit more about theory, I thought it would be neat to draw a distinction between those 2. Okay, so now that we know the minimum spanning tree is a different entity than the shortest paths tree, how do we find one? Well, to do that, I'm going to introduce an idea known as the cut property. Okay? Now, this is going to seem really strange, right? This is very different than the kind of thinking we usually do in 61B. But what we're going to do is we're going to introduce some more terms first. And so the first term I'm going to introduce is the so-called idea of a cut. So a cut is just to take a whole graph and color each vertex either gray or white, And so in this case, the cut is these 5 vertices are gray, these 3 are white. That's the cut. It's an assignment of the graph's nodes to 2 non-empty sets, the gray set and the white set. Then we'll say that a crossing edge is an edge which connects a node from one set to a node from the other set. Okay, so these are all of our crossing edges. And here's a surprising but true fact, which is that given any cut you could imagine, the minimum weight crossing edge between those cuts, chosen arbitrarily, is in the minimum spanning tree for the entire graph. So here, if my weights are proportional to the lengths of the lines, this line is the shortest, so it's in the minimum spanning tree, even though all I did was randomly make up some cut and then draw a line, check all the edges between them. So for the rest of the day, we're going to assume the edge weights are unique because it'll make the argument simpler. So let's first discuss why the cut property is true. But before we do that, oops, I forgot this was here. I want to make sure you actually know what I'm talking about, which would be a very important thing. So what you should ponder is, given this graph, which edge is going to be the minimum weight edge that crosses the cut 2, 3, 5, 6? And what I'm putting here is the purple vertices. So instead of gray and white, I'm doing purple and white. And as a hint, all of these edges, this is the list of all the edges and their lengths, aka their weights, and that will tell you, well, it'll make your life easier. Okay? So I will let you think about that. Okay. And so here we see, if we start looking through these edges, we'll go from, so here's, sorry, got distracted by outside. So if we look right here, we start looking at each of the edges in turn, and we say, does 0, 7 cross this cut? And we say, no, both white. Okay, 2, 3, both purple. Okay, 1, 7, both white. And then finally we get to 0, 2, and this is a crossing edge, and it is the minimum weight crossing edge. So we know that this is part of the minimum spanning tree. Okay, so this one right here. Okay, so how do we know that's part of the minimum spanning tree for the entire graph? Well, the argument is something like this. Actually, this is the full argument. And it's to say, it's a proof by contradiction. Let's suppose, hypothetically, that the minimum crossing edge E is not part of the minimum spanning tree for a graph. In that case, what I can note is that if we were to take the existing minimum spanning tree, so this is some graph, I have a cut here, gray and white, this is the minimum crossing edge. And so if here all the thick lines represent the minimum spanning tree, and E the minimum crossing edge, well, what I'm going to note is that if we added E to the minimum spanning tree that we've already built, right, then it would cause a cycle. And you can think about it this way, right? If we have a spanning tree, which is V minus 1 edges, and I add another edge, then it is guaranteed that we're going to end up with a cycle. Okay? Furthermore, there must exist some edge that connects these two halves of the cut. So there's some other edge in the graph that's going to be a crossing edge. And so what I can do to make the tree even lower weight is I could remove F and swap it out for E. And that's a contradiction with what we originally said. We said the minimum spanning tree does not include E, but here we've shown a process by which some better minimum spanning tree could be made. What we've done is we've shown that if we have a minimum spanning tree that doesn't include the lowest weight crossing edge, then we could remove some edge and replace it with this minimum weight crossing edge and get a better minimum spanning tree, which means the original thing we had was not a minimum spanning tree. Sorry, there's some strange drama going outside. Okay, so that's our proof of the cut property. So why is this useful? Well, it gives us a potential algorithm for finding the MST. And it would go something like this. Let's imagine we have a graph. And first we have no edges in the minimum spanning tree. So we'll start with no edges, right? That's how we start. Generally, we don't have a tree yet. And then what we'll just do is make up some cut. And that cut, if it has no crossing edges that are part of the minimum spanning tree, then we can add the smallest crossing edge to that tree, and then just repeat that process over and over. So in other words, I might take a graph like this, color some of the vertices white, some of them purple randomly, add an edge, and just keep repeating that process over and over until I finally get a tree, and that will be the minimum spanning tree. And that'll work, but we need some better way of finding a cut that has no crossing edges, because if we keep guessing randomly, it may be that the random cut we come up with, doesn't actually give us a new a new edge that we can add to our minimum spanning tree. Like just as a trivial example, suppose we keep generating the same cut over and over and over, then we wouldn't get the answer. And so we want something better than just randomly coming up with cuts, and that will be our stronger algorithms we'll be learning about next.